Well, we're starting a new topic in linear algebra, and it's the concept of an inner product space and also an inner product. And it's just a general table of contents. I'm going to start with a preface or introduction to what an inner product is and what's an inner product space. Then we'll define things a little more formally, and then we'll work through some examples. Now, very important, you have to have studied vector spaces because the inner product space builds on vector spaces. So let's get started. Okay, the preface, it's like an introduction. So an inner product is something we define on a vector space, and it's a function, and that function takes in two vectors and spits out a scalar, a number. So it's a function of two variables, and rather than giving it a letter like f or something, we have a special notation, angular brackets, and the inner product of u and v, we just mark it this way. And as I said, we take two vectors u and v, and their inner product is a scalar. But not any function which takes two vectors and gives us a scalar is an inner product. There are certain conditions. Actually, we're going to have 4 conditions, and we'll see that later. Now, we always start with a vector space. So in our first example, we'll take the vector space to be R2, the 2D space. And let's take a pair of vectors u and v, only we know what we're going to look like in R2, just a pair of numbers. We'll call it u1, u2 and v1, v2, although if we're being strict about it, we would write them as column vectors, but we already agreed that to save space, it's just more convenient to write them in a row rather than a column. Now I have to tell you how to multiply them, how to get the inner product of these two. So I'm suggesting the following inner product. We take u and v, and what we do is we multiply u1 with v1 and add to that the product of u2 and v2. Those of you who have studied physics and know what a dot product is, this is very much like a dot product. It's almost the same thing. And if you haven't heard of it, never mind. And to get very specific, let's say that u was 1, 2 and v was 3, 4, then the inner product of u and v is 1 times 3 plus 2 times 4 would be 11 with this definition of the inner product. So our function takes two vectors, this one and this one, and gives out a scalar. That's the output. These two vectors are an input, a scalar is the output. Now, I mentioned before that not any function that takes two vectors and gives a scalar is going to be an inner product. There have to be certain conditions, and now I'm going to give you the 4 conditions that it has to satisfy. The first condition is that for any u and v, the inner product of u and v is the same as the inner product of v and u. In other words, the order doesn't matter. So let's check if this condition holds with our inner product. We took u and v like so, and we computed it. Actually, we computed it earlier. Inner product of u and v gave us 11. Now let's try doing it the other way. Inner product of v and u, this time we reverse the order of the vectors, 3, 4, and then 1, 2 is 3 times 1 plus 4 times 2, and it also came out 11. This was no big surprise, because really we're getting the same products just in a different order. Instead of 1 times 3, we have 3 times 1, and here instead of 2 times 4, we have 4 times 2. Obviously, it's going to be in general true. And by the way, I should have mentioned this upside down A. I presumed you know what it is, but in case you don't, it means for all. So like here, for all u and v, and that's the set theory belongs to, for all u and v in R2, and the second rule, and for any alpha in R, alpha will be a scalar, then the inner product of alpha u with v is the same as alpha times the inner product of u with v. So if we multiply alpha by u, and then take the inner product of these two vectors, it's the same as taking the inner product of the vectors, getting a scalar, and multiplying it by alpha. So let's check. I'll take the same u and v as before. Alpha, I'll keep it general. I could have taken, say, alpha equals 7 or some number. We could, but I'll leave it as general, as a general scalar. If I evaluate this bit alpha times u, it's alpha times 1, 2, which is alpha 2 alpha. Okay, now let's see if these are equal. First, the left-hand side. Alpha u inner product with v is alpha u from here, v from here, and that's equal to this times this, which is 3 alpha, and this with this gives us 8 alpha, altogether 11 alpha. Now the right-hand side, first we take the inner product of u with v, which is this with this. And actually we've done this calculation before. This bit comes out 11, alpha times 11, 11 alpha. So we get the same result both ways. And so this second rule is satisfied. And I said there are 4